Good morning. So last lecture we looked at tangent vectors and what these things could be in the context of differentiable manifolds. And I described to you several possible approaches to generalizing this naive notion of a tangent vector that we have to the more general manifold setting. And the one that, I suppose the one that will occupy us, or the one that we'll take recourse to the most often, will be the directional derivative version of tangent vectors, although occasionally it's useful to use the other definitions. And just to remind you, if you have some function going from a manifold M to the real numbers, then one way of interpreting the word tangent vector is as a directional derivative, because a directional derivative is an object which has a direction, and if you look at the manifold as an embedded manifold, you can also see that this corresponds also with the embedded notion of a tangent vector. And so to capture that, we imagine that we had a curve and we differentiate f along that curve. So that's something we can do using standard calculus tools. So here's the picture, here's the manifold M. Here's the real line, here's the origin, here's our curve C. Here's some function to the real line. Here's a chart, phi, u. F composed C. And we're going to be looking at, we're thinking of tangent vectors as derivatives of functions along curves C. That's the interpretation, one of the many interpretations that I discussed in the previous lecture. And then in terms, because we got this coordinate system here, we could equivalently do this derivative as follows, right? We could regard f as a function of the coordinates here. First differentiate with respect to the coordinates of our chart, and then differentiate those with respect to t along the curve C. So this is how you would calculate the directional derivative of f along C, and then evaluate everything at t is naught. And then you notice, well, this is just some fixed set of numbers. Let's give them a name, say v. And we see that the space of all directional derivatives this space is n-dimensional. This is our coordinate chart here. And it's spanned by all vectors of the form v. So for every vector v in some n-dimensional vector space, we get a directional derivative. There exists at least one curve, which gives us this directional derivative and vice versa. And the kinds of vectors that live in this vector space, we write them as these slightly abbreviated form, like this. Now, d dx mu is like a basis vector for our vector space. And occasionally, we'll use the notation e mu for that differential operator here. So the tangent space at a point x, this is the point x. Actually, x is kind of a stupid notation when we have coordinates. Let's say for a point z in the manifold, when t is 0, the tangent space there is the linear vector space spanned by all differential operators that look like this, and it's exactly n-dimensional because mu is running from 1 all the way up to n. Now, this is one of the many definitions we have of a tangent space, and we'll probably use this one more often than not throughout this course, although we'll definitely use the embedded version as well. So we'll often use a different notation for exactly this thing here. I'll actually use several notations throughout this course. Also might write that as V on F. So all the tangent vectors that you could write down according to this definition at a point z equals c naught, they form a vector space. So you have to kind of work to convince yourself of that fact. So you want to show that if you have two such vectors, that their sum is also an allowed vector of this form, that any scalar multiple of them is a vector of this form, that 0 is an element of, and so on and so on. So you have to check all the requirements to be a vector space. And then after you've done that, you'll be convinced that at least at this point z in the manifold, these tangent vectors form a vector space. So we're going to give that vector space a name. We're going to write it as T, M, Z, tangent to the manifold at Z. And these basis vectors here, they're going to be called the coordinate basis, or coordinate basis. So this we covered in various forms in the previous lecture. So check that this is well defined. So if you use a different chart and have a different coordinate basis, check that an element of this tangent space is independent of the basis that you chose. So probably it will be helpful for you in thinking about this to notice the transformation law between two vectors, two charts, or two coordinate bases, so namely that ddx mu is ddy nu dy, I did it the wrong way around. I think that's correct. So the repeated indices are summed. So it's probably useful for you to notice this transformation law. And once you've worked through this exercise, then you should be happy with talking about tangent vectors at a point of a manifold and writing them in terms of a basis, which is defined in terms of a coordinate chart or a coordinate system. And this is pretty much all we need for the moment to know about tangent vectors. But before we move on from tangent vectors, I want to discuss something rather remarkable about the set of all tangent vectors to a manifold. So we know a manifold is a manifold, right? That was a part of the input data. Let M be a manifold. But what I'm going to argue now is that Tmx, or Tmz, if you take all of these Tmz's, every tangent space at every point in a manifold, and you stick them all together, then that will give you a new manifold, a bigger manifold. And that one's called the tangent bundle. And this is the most important manifold in this course. And the reason for that will become clear in about 10 minutes. So if you stick together all these vector spaces for every point in M, then you get a new manifold, a bigger manifold. And this one is called the tangent bundle, which is the title of this lecture. And we just denote that usually as Tm without the Z. Now a point in Tm. What is a point in Tm? Well, a point in Tm is, to specify it, you need to know the point in the manifold and a corresponding vector tangent to that point in the manifold. So you need some coordinates to do that, say. but let's just say it first abstractly without coordinates. So a point in Tm is, if you like, a pair of a point in the manifold and a vector tangent to the manifold at that point. So given that observation that points in Tm are pairs of vectors and pairs of points and vectors tangent to the manifold at that point, then we can actually introduce a coordinate system for this manifold. And that coordinate system is given simply by, well, the coordinate system on the manifold and coordinates of the tangent vector space. So it's actually easier to write it than say it. So there's the coordinates of a point in the manifold. And then we write out our tangent vector using the coordinate basis that I introduced just above here. Just to emphasize the point that repeated indices are summed. So every point in Tm, this tangent bundle, can be specified by a tuple of 2 times n numbers. Firstly, the coordinates of a point in a given coordinate system, and then the tangent vector written in terms of this coordinate basis at that point. This is double the dimension, if you like. There's a special map on this tangent bundle called the natural projection. This will come up multiple times. There's a nice smooth map. Tm goes to m. And how does this map work? Well, you give it a pair of a point and a vector, z, and it just gives you the corresponding point, throws away the tangent vector information. So that map is called the natural projection. Now the inverse of this map is also pretty useful, and it defines for us something called the fiber. We're not going to dwell on fiber bundles, principal bundles in this course, but it's worth at least giving you that terminology so that you will understand it if you see it. So the inverse image of a point Z, what is it? Well, it's a whole vector space. It's the tangent vector space to the point Z in M. And this is called the fiber. At the point Z. Let's do our favorite example. Just to have an example in mind. So at a point in the circle, here's the circle here, that's our manifold S1. So at a given point in the circle Z, the tangent space is one-dimensional. Isomorphic to R, the real numbers. And there's only one tangent vector because it's a one-dimensional vector space. So if we choose a coordinate theta on our circle, then points in the tangent bundle are pairs of, well, local coordinates are given by theta and d theta. So remember, this coordinate chart here only works for theta away from, say, 0. We need two charts to cover the circle. But in this particular chart, the local coordinates are given by a pair, theta and, sorry, that's better. The coordinates of the point z psi, this is a point z on the circle and some tangent vector to that point, are given by theta, the coordinate of the point z, and the coefficient of d theta when you expand our tangent vector in terms of this basis here. So d theta points in that direction. If you think of it as an embedded manifold, And the coefficient psi theta here is just telling us how long the vector is at that point on the boundary, on the circle. And so Tm, what kind of a manifold, or Ts1, what kind of a manifold is this, right? The whole bundle itself. Well, we have its coordinates. The coordinates are some point on a circle and some real number. So we actually have a manifold that has all those properties. It's S1 cross R, or otherwise known as a cylinder. So Ts1 is a very familiar manifold. It's the cylinder. This doesn't always happen that it gets so nice. So as I emphasized in the previous lectures, S1 is not trivial, and Ts1 is also not trivial. There's a lot of interesting stuff that can take place in the tangent bundle to a circle. Now I'm going to explain why we're interested in tangent bundles at all in this course. Okay, you can make definitions, we can do mathematics, but this is a course in a theoretical physics institute. Therefore, the relevance to physics is more important than the definitions. And so I'll explain now why the tangent bundle is a very useful object to define. When you're talking about classical mechanics. And here's the reason why. Tangent bundles are the natural place to do Lagrangian dynamics. Because they give you just the right amount of information to talk about Lagrangians. So I'll just remind you. So this is, tangent bundles are the right place to do Lagrangian dynamical systems on manifolds. So there's many objectives to this course. One objective is to introduce you to the language of symplectic geometry. A second is to explain why is it relevant to physics. A third is to generalize stuff that you already know to a greater set of examples. And this comes under multiple of these headings. Doing Lagrangian dynamical systems on manifolds reveals how to generalize Lagrangian dynamics to a wider class of systems. And furthermore, we'll use this as a basis for discussing symplectic geometry when it comes up soon. So let M be some differential manifold. And when you did Lagrangian dynamics before, that typically would have just been the real numbers, or R to the M. Well, now we've got a manifold, let Tm be its tangent bundle. Right? We've just introduced this object. So a good exercise is to think, what's the tangent bundle to the real numbers, for example? Should be hopefully obvious that that's R2. And so the tangent bundle to Rn should be R to the 2n. Hopefully that's clear. So imagine we got the following data. We got 3 pieces of information. We got a differentiable manifold, then its tangent bundle, which is essentially given by the definition of M. And we got a further piece of information. We got some function from the tangent bundle to the real numbers. Now this function, I've written that as L. And why have I written that as L? Well, because L stands for Lagrangian in this context. So if you think, what is a Lagrangian? A Lagrangian is a function of positions and velocities. Now, what are the elements? What are points in this tangent bundle? Well, points in this tangent bundle are pairs of positions and tangent vectors, which, according to, say, the idea of the definition of a tangent vector as a directional derivative, are like velocity vectors. So a simple ordinary function from the manifold Tm to R is a Lagrangian. So a map, we're going to also talk about the solution to a Lagrangian dynamical system. A trajectory. So a map gamma going from R to the manifold M, that's a curve, right? Remember we introduced the notion of curves. A curve is a map from the real numbers to a manifold. So a curve in the manifold M, what is it? Well, it's called a motion. This is a two-board definition. So we have some manifold, we have its tangent bundle, and we have some function on the tangent bundle. And a map, a curve in our manifold is called a motion in the Lagrangian system with configuration manifold M and Lagrangian function L if this gamma is extremal for some functional. And what that functional is this action here. So phi takes a curve and produces a number, and it produces a number according to this recipe here. Now extremal, remember what that means from your classical mechanics. It means if you make a small variation of this path, then to first order, this thing vanishes. It doesn't mean it's biggest or smallest. It just means that first order variations vanish. And in fact, you often don't, when you apply the extremal principle, the solutions are not necessarily biggest or smallest. They're just some point where first variations vanish. Now we have a nice theorem which completely, I mean, with this technology here, you can just transfer the proof from your classical mechanics course to this course. Just by taking a chart and then applying what you know about Lagrangians in that chart. So what is the theorem? The theorem says that if you take some coordinates for a point in this tangent manifold along the trajectory, so x mu t equals phi composed with gamma, so if you look at these coordinates, look at the coordinates of a point in the motion, then you can't just have any old coordinates. If it's extremal, if this motion is extremal for this functional there, then they satisfies the Euler-Lagrange equations. Well, I wrote that. Okay, that should look pretty familiar to you. So we're about to move on to a different topic, but before we do so, it's worth pausing and explaining this way of formulating dynamical systems. So in the history of physics, it's usually the case that the equations of motion of physics are written down in a very lengthy form when they're first discovered. Maxwell's equations, if you look in Maxwell's book, they're written down as dozens of equations in terms of coordinates. And similarly for various other equations of motions in physics. And then it's been discovered time and time again throughout the years that you can sort of compress these equations of motion into a much more compact form by noticing that the equations of motions of physics arise as the Euler-Lagrange equations for some function L on some tangent bundle M. So all of this, I mean, if you really didn't, if you loathed manifolds and all this sort of stuff, you could do everything in terms of coordinates and never, ever, ever take recourse to differential manifolds and write everything out as lengthy equations in terms of coordinates. But it's very helpful to realize that those equations come from something that can be written down with less space on a board, let's say. So all of the equations of motions of Newtonian physics can be understood as arising from the variational calculus applied to some Lagrangian function L, kinetic energy minus potential energy. And that is very helpful when you want to remember lots of information in a compact way. So this is a way of compactifying, compressing the equations of motions, because then you know, okay, I don't remember all the equations of motion for a bead on the surface of a sphere, but I know that the configuration space of a bead on the surface of a sphere is a sphere. I know that the tangent bundle is the correct place to talk about velocities on a sphere. And I know that the Lagrangian function is just the kinetic energy for a bead constrained to a sphere. So that's some function that I can write down or at least work out again. And then when I pick some coordinate system, I can laboriously work out all the equations of motion for the bead on the sphere. However, if you didn't want to go this way, if you wanted to just say, I hate manifolds, I'm going to do it everything from first principles, then you have to sit and work out how to derive equations of motion for a bead on a sphere by looking at a point on the sphere and a neighboring point and the forces and the restoring forces on the bead and so on. So this is a much more compact framework to capture exactly the same physical system, and there's no avoiding the hard work, but the surface area of stuff that you have to remember to get to those equations of motion is much, much less if you do it this way. I'd argue that. So that's one reason why you should worry about Lagrangian dynamical systems. And I hope as the course goes on, you'll come to appreciate this way of doing things a bit more. Okay, now we come to the next topic in this course, namely differential forms, exterior forms. Now, for some reason, this is very confusingly done in many books. Exterior forms, what I'm going to develop, and differential forms in the rest of this lecture. The reason we're doing all this is we want a notion of signed area to do integrals over. And what do I mean by signed area? Well, we want to have a notion, we want to generalize integration from our flat space setting where we're used to doing integrals to the curvy version of differential manifolds. And to do that, we need some notion that when you exchange the limits on whatever our generalized integral will be, you'll get a minus sign. Right? This is a property of integrals. This is a fundamental property of integrals. If you integrate from a to b, that's the same as getting minus the integral of going the other way along the integral contour. And similarly, in higher dimensions, if you flip the coordinates of integration one time, you get a minus sign. And if you flip them both, then you get a plus sign again, and so on. So exterior forms, differential forms, what we're going to define soon, are objects that have this kind of anti-symmetric property, that if you exchange things, you pick up minus signs. Now, there's more than one way to generalize a thing in maths, as I stressed in the previous lectures. We didn't have to do it this way. We could have generalized integration or manifolds in other ways. But this is the way that's turned out to be useful in practice. So here we have in mind tasks such as integrating a function over the surface of a manifold. So if you have some manifold M, which I'll draw as an embedded manifold, and you want to integrate a function over this manifold, then, well, it's kind of clear what you should do. Think about how we define integrals in real space, is you make some fine grid on the manifold like this, and you build a approximation to your integral, integral over M of some function f d question mark, whatever that means. So instead of using this notation, instead of using this Leibniz notation, for the moment we'll just write the integral of a function over the manifold M as an object that eats a function and gives a number. Because this notation is sort of doesn't match well with what the integral is doing. The integral is eating a function and producing a number. And how would you do that in the most naivest way? Well, you set up some fine grid, and then you approximate your function over these little squares as some linear function. And then you build up the partial sums. of the integrals over these little pieces there. You could use linear approximation, or you could use, you could just sample the function somewhere in the box. I mean, all these ways of approximating an integral will converge as you take these little boxes smaller and smaller. So you see that you can approximate the integral of a function m, integral of a function f on the manifold M. Well, it should be the case that it's equal to like sum of little squares s of the integral of the function over these little squares. But here's where things get interesting, right? Because our manifold is curvy and this coordinate system isn't rectangular, these little squares aren't squares. The word square was wrong, right? They're the inverse image of squares. You take some chart U. You know, the only place where we know how to make little squares is in Rn. So you have some chart like this. And a nice little square there pulls back to something that's not really a square. I mean, if we're thinking embedded here. This is so a little square in our coordinate chart, as an approximation to a piece of the manifold, is not really a square. It's more like a parallelogram, right? So this little square S looks like a little parallelogram here. Under phi inverse. And it's actually, I've drawn it flat, but it's not even flat, right? This little square here, when it pulls back onto the manifold, is curved. It's a curvy parallelogram. So maybe I'll draw the picture slightly exaggerated. Now, that's not very much used for doing calculus if it's curvy. So what we do is we approximate that as something flat. And then we can do integrals over parallelograms. We know how to do those. So this, to calculate this thing here, we first calculate our curvy square on the manifold, and we approximate it with a nice flat parallelogram, and then we use our standard calculus to do the integral there. And if we reverse the orientation of this parallelogram, we're going to pick up minus signs according to this rule here. So in this way of thinking, this integral box here is a way of taking two tangent vectors, because this is how you approximate a curvy square with a flat parallelogram, is you take the tangent vector at that point here, say, the tangent vector at that point here, and you build a parallelogram tangent to that curvy square. So this integral here is an object that eats tangent vectors and is anisymmetric under exchanges of directions. So the exterior forms that we're going to discuss now, they're going to take this idea of being objects that eat tangent vectors and give us numbers and that are antisymmetric. Those are the properties that we're going to take to build things called exterior forms or differential forms, and these are the objects we're going to use to build integrals on manifolds. So this is one way you could build integrals on manifolds. It's not the right way. It'll turn out to match other ways you could think of doing it. and it will turn out to generalize our notions of integration in a natural way. So let's get to it. We need to first talk about things that can eat tangent vectors and give us numbers. What sort of things can eat tangent vectors?
Question.
Yeah.
To this idea. So the idea is that we kind of want to define a measure using the volume in the embedded space.
Yes.
Right? Okay.
Here the question was, is the idea that we wanted to find a measure using the volume in the embedded space? Yes. Yeah, that's the idea. Although I'm going to steer clear of saying the word measure. We're not going to generalize integration using measure theory in this course. We're going to generalize the standard calculus rule for defining Riemann sums.
Is because explained, not defined, but explained this integral over m by an integral over s. But for me, it looks like that we kind of take the volume of s there and the constant in s. So this would be then the measure of, the measure of s, right?
So it looks like, the question is, it looks like this is the volume of S here?
Yeah, or it should be to explain the left side.
To explain the left side, yes. Okay. Yeah, roughly speaking, yes. This is extremely metaphorical. Yes. Yeah. This is a motivational piece for the actual definitions that are about to come. All right, definition. We need things that can eat tangent vectors and give us numbers. I'm going to give such a thing a name. Well, they're called dual vectors if you like linear algebra, but in this context they're also given another name. They're called forms of degree 1 or one forms. And it's a linear function omega from Rn, the vector space Rn to R. It's just what they're called. I mean, sometimes we have different words for the same thing. And in the context of a linear algebra course, I would never use the word form for such a thing. I'd just say, let omega be a linear function from Rn to R. Because it's a linear function, if you take a linear combination of two vectors, well, it's a linear combination of the form evaluated on these two vectors. So the space of one forms, well, is the space of linear functions on Rn. We have another name for that. It's called the dual space. And we have another notation for that, Rn star. It's probably the notation you're familiar with. So if we have a coordinate system for Rn, just a standard rectangular coordinate system, then each of these n functions, x1 through xn, they're linear functions on Rn, so they give us one forms. Furthermore, they're linearly independent. And they give a basis for this dual space. And so what basis means is that if you have an element of a vector space, you can always write it as a linear combination of the basis. Oh no, I've written it with downstairs indices. Yeah, okay, I think that's important. This distinction matters a bit later on. So you can write every linear function on Rn as a linear combination of these basis forms here. Okay, so far so boring, right? We're just talking about linear functions on Rn. Things get interesting when we go to the tangent space to a manifold. Because there, what we have is a vector space. The tangent space to a manifold is always a vector space, and it's always isomorphic to Rn for some n. But if we want to generalize integration, remember we need some way of eating vectors and producing numbers, and moreover, eating more than one vector. So we're going to have to introduce a couple of notions before we'll be able to do that. So we'll start by generalizing the notion of a form to not just one vector space, but the union of all the vector spaces tangent to a manifold. It's our first task. So at the moment, this is just at the level of words and definitions. The dual space to the vector space TMZ. Remember the set of tangent vectors at a point Z in a manifold is a vector space, so there's a dual space. Is going to have a name, it's going to be called the cotangent space. So whenever you have a dual of something, whenever you have functions on a thing, it's usual to put the word co in front of it. And just to state the full consequences of what that means, an element of the cotangent space at Z is a linear function omega at Z from Tm of Z to the real numbers. And we're going to give it a name. Such a thing is called a cotangent vector or dual vector. So a cotangent vector or a dual vector, what is it? Well, it's something that eats tangent vectors for breakfast and gives you numbers in a linear way. That's all you need to worry about at this stage when you hear the word cotangent vector. Now, there's lots of interesting examples of cotangent vectors. I'm going to show you one right now, the most important examples. This is the example that's so important it motivates the definition. So let M be a manifold. A circle, the sphere, something else. And let F be some function on the manifold. Okay, so far so familiar. Well, we know that vectors in the tangent space can be thought of to this manifold as differential operators. It's up to you. You can choose to think of a vector in the tangent space as an operator on functions. So the vector v, what does it do? Well, you give it a function, and then you directionally differentiate the function along the curve whose coordinates match v in the chart of interest. Now what I'm going to do is define a linear function on vectors. So we're going to use the symbol df for this cotangent vector. I mean, you've done many variable calculus. df has a certain meaning to you already. And we're going to use this notation for this cotangent vector directly to match with that meaning that you already understand. When you first wrote down df, however many years ago you wrote it down, I certainly don't think you were thinking of it as being a cotangent vector acting on tangent vectors. So df is like the increment, right? If you change a many variable function by a little bit in terms of its arguments, then df tells you the change in the function. But here we're going to define this symbol here to act on tangent vectors. And how do we do it? We're going to introduce a pairing which is defined simply to be do v on f. So I've used several different notations for exactly the same thing. So this is really a fundamental example here of a one form. So a one form on a manifold is a linear function on the tangent space. Okay, so that means that you give it a tangent vector, it will give you a number. And this symbol df, well, if you define df of v to simply be v applied to f, then you definitely get a number. That's the directional derivative of f. But here you think of the role of the operator and the argument in reversed. So here, when you look at this, you think of the tangent vector as acting on the function to give you a number. But here we think of things in the opposite direction. We think of the function as giving you something that then eats a vector and gives us a number. And that something is what df is defined to be. df is a one form, a cotangent vector. It eats a vector v, gives us a number, and the number it gives us is nothing other than that, or this. And so these are all multiple notations for the same thing. So you can either think of f as acting on v via this df, or v is acting on f. Definitely a linear function. So it satisfies all the criteria to be a cotangent vector. We can do all of this in terms of coordinates, right? We're sort of halfway there. So this thing df, which is part of the cotangent space of our manifold at the point z, we can express that as a linear combination of basis vectors, basis cotangent vectors. I introduced that basis just before. And it turns out that we can write that basis with this notation here. This notation is coherent. Yep. Let's first define this basis E mu . So E nu, remember that? That was this basis for the tangent space at the point Z. And E mu is defined by that equation there. And it so turns out that E mu is actually equal to dx mu. So x mu is a function on the manifold. It's a particular function on our manifold. We can take its d. So any, remember, this object d, you have df is you give this thing a function and it produces for you an element of the cotangent space. So dx of mu is none other than doing just that. X mu is a function on our manifold. Dx mu is a cotangent vector defined according to that expression over there. And it'll turn out to be none other than this abstractly defined E mu here. So we have two ways of defining a basis for this cotangent space. And we'll see that they're the same thing. To see that, we'll just notice that suppose f equals the coordinate function x mu, then we have that dx mu, the way it's defined to act on a vector v, is according to that formula there. So that's exactly the same action as these abstractly defined vectors there. And that's why we regard these dx mu as a co-basis or dual basis for T star mz. This also means that an arbitrary one form, omega, can be written as a linear combination of these things. Good. I think we will stop here for today. So in the next lecture, this is not quite our goal of generalizing integration over manifolds. In fact, that will take a couple of lectures to get that fully working. But what we have achieved is defining a notion of oriented signed area for at least one-dimensional manifolds. We haven't quite expressed it that way today. In the next lecture, which will take place next week because tomorrow is the exercise class, we will find a way to build functions of pairs of vectors, of triples of vectors, and that will require us to introduce something called the tensor product. But for now, we'll stop here, and I thank you very much.